Hey there, math fans. Quick intro to the 3D coordinate system. A few little notes, things you're going to need for the homework. So let's take a look. So here's the 2D coordinate system. There you might be familiar with these terms of first quadrant, second quadrant, third quadrant, fourth quadrant. You might know a few things like if I give you a point on the x-axis, what do we know about it? If it's on the x-axis, the y has to be 0, and x can be anything you want. So this is what it means to be on the x-axis. And similarly, what does it mean to be on the y-axis? Well, the x has to be 0, and the y can be anything you want. So that's kind of a quick review. In 3D, there's that this tends to make people uncomfortable, but it's not really that bad. I know that the first quadrant is when all the numbers are positive. I had to look this up because we don't use other octants. Sorry, we say octants because there are 8 of them. This is a picture that a student made for me last term. But I guess they number them this way. This is all the positive z's. But I've never referred to anything besides the first octant. And then it does the same kind of counterclockwise thing from there. As you move into 3D, I find that if you had discomfort with, what is the x-axis, it gets worse in 3D. So you really have to think in terms of conditions. Okay, so briefly, the condition for what it means to be on the ground, to be on the xy plane, is that x and y can be anything you want, but z has to be 0. So this is what it means to be on the xy plane. Now casually we like to just say z has to be 0. Now if you're on the x-axis, that's a different story, because if you're on the x-axis, both y and z have to be 0, and x can be anything you want. So this will come up in some of your homework questions, being able to think about what we have. All right, the main tool, initial tool we have in 3D is the distance formula. Now you may or may not remember the distance formula in 2D, but I'm going to do a quick recap, just a tiny bit of theory here because it doesn't take very long for me to do this. So it all boils down, the distance formula, if you didn't realize, was the Pythagorean theorem. So if you don't know the Pythagorean theorem, I can do that for you too, but I better not try to fill one video with too many things. So the Pythagorean theorem talks about a right triangle here and the relationship between those sides. Make this a little smaller. Okay, so you get a squared plus b squared is c squared. In fact, that's when the scarecrow gets a brain in the Wizard of Oz. That's what he says. The square of the hypotenuse is the sum of the square of the other two sides. Okay, anyways, there is a right triangle here. This change in x, what I'm labeling is, if I knew what this point is, let's pretend this is 1, 2, 3, and let's pretend the other point down here is 0, 0, 0, and I want the distance between them. Let's talk about a few things. The corresponding point that's right below it is going to have a z coordinate of 0, but the other two coordinates are going to be the same. The corresponding point over here is going to have both the y and the z be 0, but the x is going to be the same. So there's our first example of kind of corresponding points that line up. There is a right triangle on the ground here. And there's this side, which we don't care about, that we can say something about. So we can say the change in x, which in this case is 1 squared, plus the change in y, which in this case is 2 squared, equals that unknown question mark squared. We probably should give it a label. But the clever idea is that there is another right triangle here looking like this. So this is why I like to, we don't do a lot of proofs in this course, but it's just so nice. So if you take the question mark, you square it. You take the change in z, which is 3, you square it. You get the desired distance squared. And we finish off getting the 3D distance formula by just substituting. Rarely do things work out that nicely in math. Okay, so what we conclude is that the change in x squared plus the change in y squared plus the change in z squared, and I'm about to run into my head here. Oh, let's move this over. Let's move my head to the top. Okay, is equal to the distance squared. So that gives us our so-called distance formula. The distance is the square root of the change in x, which we could write as x2 minus x1 if we wanted, plus y2 minus y1 if we wanted, plus z2 minus z1. So it's our first example of extending something we knew in 2D to 3D. That's really valuable because in 3D, as things get harder to visualize, it's nice that we still can compute straight line distances. Okay, so I'm going to end that there. That's a quick intro, and then I'll make a separate video where I talk about some of the homework.